Welcome to this lesson on cyclic quadrilaterals. At the end of this lesson, you will be able to define concyclic points and cyclic quadrilaterals. You will be able to illustrate that the sum of opposite angles of a cyclic quadrilateral is 180 degrees. You will also be able to illustrate that if the sum of opposite pair of angles in a quadrilateral is 180 degrees, then the quadrilateral is cyclic. Here we have three friends, A, B and C. Wherever they stand, they say that they are standing on a circle. Is this true? Let us freeze them in this position and find out. We will know they are telling the truth if we can draw a circle passing through the positions of A, B and C. Okay, let us begin with the construction. First, let us join AB and BC. Next, let us mark the midpoints of AB at M and BC at P. Now, let us draw a perpendicular at M. What does this line MN represent? MN is the perpendicular bisector of AB. Now, let us draw a perpendicular at P. Here PQ is the perpendicular bisector of BC. The perpendicular bisectors of AB and BC intersect at O. What can you say about the lengths OA, OB and OC? They are equal because any point on the perpendicular bisector of the line segment is at equal distance from the endpoints of the line segment. Since A, B and C are at equal distance from O, a circle drawn with the center O and the radius OA will pass through all the 3 points A, B and C. So, the three friends were right after all. Wherever they stand, a circle can be drawn passing through their positions. Points in this case, A, B and C, that lie on the same circle are called concyclic points. Can we conclude that 3 points are always concyclic? No, this does not always hold true. For example, let's consider 3 points that are collinear. A circle can be drawn through any 2 points, but the third will fall either inside or outside that circle. Based on this observation, we can conclude 3 points are concyclic only if they are not collinear. Uh-oh, we have another friend of A, B and C who wants to stand on the circle with them. Now, where should D stand? Let us find a position for D, so that we can draw a circle that passes through the positions of all the 4 friends A, B, C and D. This calls for some construction. First, let us join AB, BC and AC. Now, let us measure angle ACB. In this position, angle ACB is equal to 70 degrees. Now, we are very close to finding the correct position for D. We just find another point that makes the same angle as angle ACB with AB. In this case, we find another point that makes an angle of 70 degrees with AB, and that is where D should stand. D has found his position. Like his friends A, B and C, he is also standing on the circle. Based on the observation, we arrive upon the theorem which states if a line segment joining 2 points subtends equal angles at 2 other points on the same side of the line segment, then all the 4 points are concyclic. Let's prove this theorem. Here AB is a line segment that subtends equal angles at C and D. We have to prove that A, B, C and D lie on the circle. Let us use the construction we did earlier to draw a circle through points A, B and C. For proving the theorem, let us suppose that the circle drawn through A, B and C does not pass through D, but intersects AD at D dash. If the circle through A, B and C passes through D dash, then angle ACB is equal to angle AD dash B. This is because the angles subtended by a chord in the same segment of the circle are equal. But it is given that angle ACB is equal to angle ADB. Thus, angle AD-B is equal to angle ADB. This is possible only if D' coincides with D. What does this mean? This means that A, B, C and D are concyclic points. Thus the theorem is proved. What do we get if we join four concyclic points A, B, C and D? We get a quadrilateral ABCD. Now this quadrilateral is special. All its vertices lie on a circle. A quadrilateral whose vertices lie on a circle is called a cyclic quadrilateral. Here is a very interesting property of cyclic quadrilaterals. Let us measure the opposite angles BAD and BCD. Note that their sum is equal to 180 degrees. Now measure the opposite angles ABC and ADC. What do you observe? Their sum is also equal to 180 degrees. Let us verify the results for another cyclic quadrilateral. Next, let us measure the opposite angles BAD and BCD in this quadrilateral. Note that their sum is equal to 180 degrees. Similarly, measure the opposite angles ABC and ADC. Their sum is also equal to 180 degrees. This way you can illustrate the theorem that in a cyclic quadrilateral, the sum of opposite angles is always equal to 180 degrees. You can also illustrate the theorem that if the sum of opposite angles of a quadrilateral is 180 degrees, then the quadrilateral is cyclic. Here is a simple quadrilateral, a square ABCD. We know that all angles of a square are equal to 90 degrees. This means that the sum of its opposite angles is equal to 180 degrees. Let us see if we can draw a circle that contains all its vertices. If we draw perpendicular bisectors of sides AB and AD, we find that they intersect at a point O. If we draw a circle with center as O and radius equals OA, we find that the circle contains all the vertices of the given quadrilateral. Through simple construction, you can also illustrate that a quadrilateral is cyclic if the sum of at least one pair of its opposite angles is equal to 180 degrees.